Okay, so lately we've been hearing a lot about semiconductors.
Yeah,
It seems like it's one of those words that's moved from, the tech pages to the front page headlines.
absolutely.
Um, but today we're going beyond the hype. We're going deep.
Yeah.
You and we are diving into the fascinating world semiconductors.
Buckle up.
And trust me, it is a wild ride.
It really is.
To help us navigate this world, we are starting our deep dive with a real treat.
Yeah.
A Nobel Prize lecture by John Bardeen from 1956.
Wow.
Now, this isn't just any lecture.
Right.
This is a roadmap
Okay.
to understanding the birth of the transistor,
Which is everything.
the invention that quite literally revolutionized everything.
It's fascinating how Bardeen, even while accepting the highest scientific honor, he emphasizes that this breakthrough wasn't a solo act.
Right.
It was the culmination of decades of research, a global relay race of brilliant minds passing the baton of knowledge.
I like that, passing the baton.
Yeah.
So let's rewind the clock a little bit here because we're talking about a lecture from 1956. Let's go back even further to the 1930s and 40s.
Okay.
What was the state of the electricity game back then?
Yeah.
What were those early pioneers tinkering with?
So they were wrestling with materials like copper oxide and selenium, trying to unlock their secrets.
Okay.
Imagine even then they saw glimpses of a future driven by electronics.
Wow.
They were laying the foundation for the digital age without even realizing it.
It's like they were piecing together a puzzle
Yeah,
without knowing what the final picture would be.
exactly. They knew these materials, these semiconductors, held immense potential.
Okay.
They could control the flow of electricity in ways that metals couldn't,
Huh.
but they didn't fully understand why or how.
So how do we go from those early experiments
Yeah.
to the tiny chips that power our smartphones?
It all boils down to understanding and manipulating a semiconductor's most important characters,
Okay.
electrons.
Okay.
You see in a conductor, like copper wire, electrons flow freely, like cars speeding down a multi-lane highway.
Yeah.
Insulators, on the other hand, are like roadblocks. Electrons can barely move.
Yeah.
Semiconductors, however, are the clever traffic managers of the material world.
Oh, interesting. So they can control the flow, like traffic lights.
Precisely. And that control comes from a special trick, doping.
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 Okay.
Imagine adding a pinch of spice to a recipe and completely transforming the flavor.
Okay.
That's what doping does to a semiconductor.
Huh.
By introducing specific impurities, they could dictate whether a semiconductor had an excess of free electrons or, even more intriguing, holes.
Holes, like actual holes in the material.
Not quite. Think of it like this. Imagine a parking lot with one car missing.
Okay.
That empty space, the hole, becomes just as important as the cars themselves
Right.
because it allows them to move.
Okay.
In a semiconductor, these holes are like those empty spaces, and they can carry an electrical current, just like electrons can, but with a positive charge.
Okay, that's pretty mind-blowing.
Yeah.
So by carefully choosing what spice to add, they could essentially tune the semiconductor
Exactly.
to have more electrons or more of these holes.
And that's where things get really interesting.
Yeah.
Because this ability to control the flow of charge carriers, those electrons and holes, is the bedrock of all modern electronics.
Wow.
It's the key to creating the transistors that power our computers, our phones, even our coffee makers.
So before we get to the transistors,
Yeah.
I want to go back to something you said earlier, silicon and germanium.
Okay.
Why did those two materials become the superstars of the semiconductor world?
Turns out silicon and germanium have this Goldilocks quality when it comes to their electrical properties.
Okay.
They're not too conductive, not too insulating.
Mm-hmm.
They're just right for creating those controllable pathways for electrons and holes.
Uh-huh.
Plus, silicon is incredibly abundant. It's literally found in sand.
So we're talking about taking something as common as sand and turning it into the brains of our devices?
It's incredible.
That's incredible.
But there's a catch, you see.
Okay.
Even the tiniest impurities, like one unwanted atom in a billion, can throw off the whole system.
Oh, wow.
Imagine finding a single grain of salt in a whole bag of sugar. That's the level of purity they needed.
Wow. Talk about a high-stakes baking competition.
Right.
They were basically trying to create the perfect semiconductor souffle.
And those early pioneers were incredibly resourceful.
Yeah.
They developed ingenious methods to purify silicon and germanium to an almost unimaginable degree. But even with these ultra-pure materials, there were still some mysteries lurking just beneath the surface. Literally.
Just beneath the surface.
Literally.
Okay, you're really setting the stage for a good mystery here.
Yeah.
What were these mysteries?
Yeah.
And how did they impact the development of the transistor?
Scientists had this very elegant theory called the field effect.
Oh.
And the idea was that you could control the flow of electricity in a semiconductor just by applying an electric field across it.
Mm.
Almost like opening and closing an electric gate.
Okay, so far so good, right?
Right. Sounds straightforward.
Yeah, what was the problem?
The problem was those pesky surfaces. You see the atoms at the very surface of a material.
Uh-huh.
They behave a bit differently.
Okay.
They have different bonding patterns, different energy levels. It's like they're living in a whole different world down there at the surface.
Yeah, a bit like how a beach town has a totally different vibe than, say, like a bustling city, even though they're technically part of the same country.
That's a great analogy.
Yeah.
And those surface atoms, they were throwing a wrench in the works.
Okay.
They were trapping the electric charges, making it nearly impossible to control the flow reliably.
So those early attempts at building a transistor, they hit a wall because of these rebellious surface atoms.
Exactly. It was beyond frustrating.
Wow.
But instead of giving up, researchers rolled up their sleeves and dove headfirst into this new puzzle
Okay.
of trying to understand the very strange world of surface states.
And this is where Bardeen comes back into the picture, right, with the transistor.
He does, but keep in mind, even Bardeen, with his 2 Nobel Prizes, didn't just magically solve the puzzle overnight.
Right.
It took years of meticulous research, a series of brilliant insights, and even a healthy dose of serendipity.
Okay, so spill the tea. What were some of those key aha moments that led to that breakthrough?
One of the big game changers was a technique using electrolytes.
Electrolytes. Now, when I hear electrolytes, I think of like sports drinks and Gatorade.
I know, right?
I'm intrigued. Tell me more.
We're talking about something much more sophisticated here.
Okay.
Imagine using a tiny, precise droplet of a special electrically conductive liquid,
Okay.
the electrolyte, to interact with the surface of the semiconductor.
Hmm.
By applying a voltage to this droplet, they could manipulate the electric field right at the surface
Huh.
with incredible control.
So they were fighting fire with fire, using electricity to tame those unruly surface states.
Precisely, and here's where the real magic happens.
Okay.
By carefully tuning that electric field, Bardeen and his team discovered something amazing.
What?
They could actually invert the type of conductivity near the surface.
Invert, you mean like turning on a light switch on and off?
Yeah, better.
Okay.
Remember when we talked about doping?
Yeah.
How you can make a semiconductor with more electrons N-type or more holes P-type?
Right.
Well, using this electrolyte technique,
Yeah.
they could create a thin layer near the surface where the dominant charge carrier switched,
Okay.
essentially flipping a P-type layer to N-type or vice versa, just by tweaking the electric field.
This is blowing my mind. So they found a way to control the very essence of the semiconductor at the most fundamental level.
It was a pivotal moment.
Yeah.
They had stumbled upon a way not just to control the flow of electricity, but to amplify it.
Wow.
And that is the birth of the transistor.
Okay, so walk me through this. How does controlling a thin layer on the surface translate into this incredible amplification effect?
Picture this. You have a small stream of water,
Okay.
and you want to control a much larger flow.
Okay.
A transistor is like a valve that lets you do just that.
Okay.
The small stream is like the input signal,
Mm-hmm.
and the large flow is the amplified output. By carefully manipulating that thin layer on the semiconductor surface, they could create a gate that controlled how much current flowed between 2 other regions called the source and the drain.
So a tiny change at the gate,
Yes.
thanks to that special surface layer, could lead to a huge difference in the overall current flow. That's incredible.
And that's the beauty of the transistor.
Right.
It's this elegant dance between material properties,
Yeah.
electric fields, and those mind-bogglingly tiny surface states.
Yeah.
It's a testament to the power of human ingenuity and the relentless pursuit of understanding the universe at its most fundamental level.
So those early transistors, the ones that Bardeen and his team developed, we've kind of seen how they changed the game, but how did they build on that groundbreaking invention? What came next?
Well, you remember those early attempts at the field effect I mentioned before?
Yeah.
The ones that got stymied by those pesky surface states?
Right.
Well, it turns out those ideas didn't just disappear. Scientists kept experimenting, kept refining their understanding of these materials. And with that knowledge, they revisited that field effect idea with fresh eyes.
So they were basically going back to the drawing board armed with, a whole new arsenal of knowledge and understanding.
Exactly. And they found that by carefully engineering the materials, by really getting a handle on those surface effects, they could actually make the field effect work.
Wow.
And this led to a new type of transistor,
Okay.
the field effect transistor, or FET.
So now we have two types of transistors.
That's
The
right.
original one that Bardeen kind of, develops and patents,
Yeah.
and then this newfangled field effect transistor.
Right, and both have been incredibly important.
Okay.
The original transistor, the bipolar junction transistor, is still used in a lot of applications.
Okay.
But the field effect transistor, especially a type called the MOSFET,
MOSFET.
the metal oxide semiconductor field effect transistor.
That's a mouthful.
Yeah, it's a mouthful, but it's a big deal. They're incredibly efficient. They use very little power, which is crucial for everything from smartphones to laptops. Plus, they can be made incredibly small, allowing us to cram billions of transistors onto a single chip.
Billions. That's mind-boggling.
It's astonishing.
So where do we go from here? What does this all mean for the future of semiconductors?
Well, the exciting thing is semiconductors are still evolving.
Yeah.
We're constantly looking for ways to make them smaller, faster, more energy efficient.
Okay.
New materials are being explored, new architectures are being designed, and the possibilities seem endless.
So that means even smaller devices, even faster internet, even more possibilities.
Exactly. The smartphones we have in our pockets today have more computing power than the masses of computers that filled entire rooms just a few decades ago.
It makes you wonder what the world's going to look like in another few decades.
I know, it's really incredible.
So you might be thinking, why should I care about transistors?
Yeah.
But remember, everything you use, from your phone to the lights in your home to your car, probably relies on the principles that we just explored.
And what's so fascinating here is that it all started with this simple curiosity about the behavior of materials.
Yeah.
The breakthroughs we've been discussing, they were the results of decades of research. It's a testament to the power of scientific inquiry and its impact on our lives.
It really is. So next time you look at your phone or your laptop or even your smart refrigerator, think about the history of semiconductors, those tiny particles that power our modern world.
It's a story of innovation,
Absolutely.
collaboration, and this relentless pursuit of understanding the universe around us.
And that's what this deep dive is all about.